Hi, everyone. My name is Frances Quigley. I'm a second year PhD student in Dr. Lewis Jones' ultramicroscopy group in Trinity College Dublin. And my talk is on to monochromate or not to monochromate, balancing electron dose and energy spread requirements. So, what is the motivation behind my work? Well, spherical aberration correctors are increasingly more common in the scanning transmission electron microscope. For spherical aberration corrected STEM, chromatic aberration can limit the resolution, and this is especially true at low voltage imaging, particularly for 2D materials. One main solution to reducing chromatic defocus blur is to reduce the energy spread of the impeding electrons via changing your electron source or installing an electron monochromator. However, this requires a balance between electron dose and energy spread requirements. So, how can we determine this balance? Well, an image simulation package was used to simulate STEM images at various different imaging conditions. The simulations were compared using a quantitative metric of image signal to noise to capture the effects of monochromation, dose, and choice of objective lens. And analysis of the simulated results will advise the instrumentation choice for those using low voltage imaging in the cost conscious landscape of scientific infrastructure. So, just a quick aberrations recap. The performance of a lens depends on the cumulative effects of spherical and chromatic aberration, as well as the diffraction limit, which is represented by these three equations here. These equations were plotted on a graph of the log of the beam radius versus the log of the beam convergence semi-angle. By plotting the sum of these equations, we see from this green line here, and by point one, that it's in fact the diffraction limit and spherical aberration that limits the ultimate resolution of your microscope. However, if you were to install a spherical aberration corrector into your stem, you'd find that this line is shifted downwards to this blue dashed line. Looking at point two here, it's actually chromatic aberration that will limit your ultimate resolution. If you were to go one step further and add in a chromatic aberration corrector, it would then be the C5 limit that would limit it ultimately. However, looking at this equation for chromatic aberration, we see that the chromatic to focus blur is inversely proportional to the energy of the impeding electrons. So for low voltage imaging, the chromatic defocus blur can be an issue. 2D materials are prone to knock-on damage when imaged at high voltages in a STEM, so chromatic aberration can be a real issue for low voltage imaging of 2D materials in a spherically aberration corrected STEM. So how can we mitigate this chromatic aberration? Well, there's three main solutions. The first is to add a chromatic aberration corrector. The second is to use a STEM with a smaller objective lens CC coefficient. And the third is reducing the energy spread of the impeding electrons. As I said, you can add a chromatic aberration corrector to reduce the chromatic to focus blur, but these can cost you up to 500,000 to install into your microscope. They require extra training for the operator. And from a simulation perspective, it's the same as using a STEM with a lens with a small CC coefficient. So, because of complexity of operation, we're not going to consider these, and we'll look at only the following two remaining solutions for our simulations. So the second solution for mitigating chromatic aberration is to use a stem with a smaller objective lens CC coefficient. So the smaller the focal length of your objective lens, the smaller the CC and CS coefficients. So if you want a really small CC coefficient, you might use an ultra high resolution objective lens. However, this would be at the expense of sample tilt range, EDX collection efficiency, and the use of certain in situ specialist holders. We're going to, in our work, we run the following simulations at a range of CC coefficients to demonstrate how a variety of different objective lens affects the resolution of the images. So the final main solution to mitigating chromatic aberration is to reduce the energy spread of the impeding electrons. This can be achieved by reducing the energy spread at the electron source, for example, replacing your Schottky field emission gun with a cold field emission gun. Alternatively, you can reduce the energy spread after electron production by installing an electron monochromator. However, monochromation leads to beam attenuation and one can lose signal to noise ratio. So what I mean by this is demonstrated in a graph made by Hackdell et al. They plotted the EELS spectra of the zero loss peak for a cold field emission gun in black here. And you see the full width half maximum of this peak is actually the energy spread of the cold field emission gun. As the electrons are monochromated, represented by these colored lines, you see that the full width half maximum decreases, as does the energy spread. However, the area under the graph also decreases, indicating a decrease in current. For example, an energy spread of 25 millielectron volts, only 3% of your initial current is remaining. And while one can scan slower in order to try account for this, this can lead to other instabilities such as environmental instabilities. We also want to take into account the cost implications of reducing the energy spread. So we plotted a graph of the approximate price of different equipment versus their electron energy spread. Of course, the thermionic electron guns are going to have the largest electron energy spread, but are the most inexpensive. A cold field emission gun has the lowest electron energy spread of all the electron sources, but is the most expensive due to a more complex pumping system and more complex in general. And finally, if you want a really low electron energy spread, you might install a monochromator into your microscope, but this could set you back $500,000. And as I said previously, monochromators do attenuate your beam, so you should take that into account. So how did we take all these variables into account? Well, as I said previously, we ran simulations and we used actually Prismatic to run these simulations. Prismatic is an open source GPU accelerated STEM simulation software. It currently supports spherical aberration, but it's not previously integrated chromatic aberration, source size, or Poisson noise. Prismatic 2.0 now includes all these features, which we use for these simulations. So it included chromatic aberration via the weighted sum of a normalized Gaussian distribution of the foci, as seen here. It also includes finite source size via 2D convolution and Poisson noise as the per pixel random Poisson draw. So using Prismatic, we plotted graphene, and we plotted a monolayer of graphene with defects. And the reason we did this is that graphene is really prone to knock-on damage when imaged at high voltages, so it's a good candidate to look at low voltage imaging. We simulated it at 30 kilo electron volts and for three different chromatic aberration coefficients represented by these three different rows, and also for 11 different energy spreads, 4 of which we're showing here at each column. So we see with an energy spread, the largest energy spread is that of the Schottky FEG that we've simulated. With the largest CC coefficient, which would be this simulation here, it has the lowest signal to noise ratio because the chromatic aberration is such a large effect on it. So one would expect for the lowest electron energy spread and the lowest CC coefficient, you'd have the highest signal to noise ratio of your image. And this isn't exactly the case because, as I said previously, the more you monochromate your beam, the more the current reduces. So you can see here, you do have to strike a balance between the energy spread and the current reduction. We also simulated these images at 15 kilo electron volts, and you see that they follow a similar trend, except for the fact that the images in general just look slightly worse because you're at a lower electron energy and chromatic aberration is just going to have that bit larger of effect. So in order to quantitatively evaluate these results, we plotted their signal to noise ratio of each image versus their energy spread. We find the signal to noise ratio is the root mean squared of the amplitude of the signal divided by the root mean squared of the amplitude of the noise. And you see that they produce these graphs here for the different CC coefficients. Looking at a CC of 3 millimeters, we see that for a large energy spread of a Schottky FEG, the signal to noise ratio is relatively low. However, as the energy spread decreases, the signal to noise ratio increases until it peaks, and then it will plummet as the current is being reduced, and therefore the signal to noise ratio will be decreased. We also note that the lower the CC coefficient, the higher the overall signal to noise ratio. This is a similar feature in the simulations at 30 kilo electron volts. And one thing that's really interesting to note in each of these graphs is that for a CC coefficient of 1.1 millimeter, at the energy spread of a cold FEG, the signal to noise ratio is higher than that of the signal to noise ratio of the peaks of the higher CC coefficients. And this would imply that if you have a high resolution objective lens with a low CC coefficient, you don't necessarily need to buy a monochromator in order to get really good high signal to noise ratio images. You could simply upgrade your Schottky FEG to a cold field emission gun. So in conclusion, in a spherically aberration corrected STEM, the optimal equipment to utilize where tilt is not necessary or when imaging 2D materials at low voltages is a high resolution objective lens with a small CC and a monochromator which selects the energy spread which suits the chosen objective lens. If, however, the cost of a monochromator is an issue, a cold FEG and an ultra high resolution objective lens can also be chosen for similar performance. And image simulation software can be a very helpful tool when trying to determine the quality of images produced in STEM versus the cost and accessibility of the equipment. I'd like to thank my supervisor, Dr. Lewis Jones, and the staff of the AML, as well as everyone in the Ultra Microscopy group for their help and support throughout the project, especially Patrick McBain, who ran all these simulations. And I'd like to thank our funding bodies as well. I'd also just like to plug that we have a fully funded 4-year PhD position in high precision imaging and high frame rate and low dose DPC STEM. If anyone's interested, feel free to contact my supervisor. Thank you very much, everyone, for listening, and welcome to any questions.
Thank you very much for that talk, Frances.
Thanks.
The questions are just starting to come in the chat now. The first one I can see is from Cameron O'Byrne. Very good talk. Is there a reason why you chose not to use multi-slice for this research?
Yeah, so that's a really good question. So we chose Prismatic, which uses the PRISM algorithm. And the reason we decided to simulate it with the PRISM algorithm is that, well, it's slightly less accurate than multi-slice. Computationally, it's a lot faster. So we decided, because we're simulating so many images, it's better to just use the faster algorithm in that case, just for that small trade-off of a slightly more error in your computation. But Prismatic can actually run the multi-slice algorithm. So these all could actually be repeated with multi-slice, but it would just take far longer, and we'd probably need better computers for it.
That seems like a good reason to make that choice. And as a follow-up question, would your conclusions hold the same, do you think, if you switch between, say, bright field, dark field, or typography results?
Yeah, so that's a really interesting question. We define signal to noise ratio in a certain way here obviously for ADF. And currently we're actually looking into how we would define that for bright field, but that's not quite clear to us at the moment, but it's something that we're definitely looking into. And so I can't draw conclusions yet, but I would think it would be something similar, yeah.
If there are any further questions, perhaps you can chase them up in the chat box afterwards. And in the interest of time, thank you very much for your presentation. You can stop sharing your slides now. And our next speaker is Peng Wang from Nanjing University. And he'll be speaking on low voltage 3D electron tachographic phase imaging.